Viscosity of a fluid is an important property that gives us a quantitative measure of fluid flow. Let's imagine that fluid is made up of different layers, and we are going to assume that the very bottom layer, as shown in this figure, sticks to the wall. So in other words, it doesn't move. In fact, we call this a no-slip boundary condition, and all fluids actually satisfy this condition. So we have this imaginary fluid with different layers, and the very bottom layer is sticking to the wall, whereas the top layer is where we apply a shear force. So the top layer is going to move in the direction in which the force is applied, and the layer that is right underneath the very top layer will also move because it is being dragged to the right hand side, and similarly the layer that is below that second layer is also going to move, and so on. So if we try to draw a velocity profile that will tell us the velocity of different layers, we know that the very bottom layer will have zero velocity because it is sticking to the wall, and then the layer above that will have a certain velocity as expressed by this arrow, and then a higher velocity, and so on, and the highest velocity will be for the very top layer. So here is a velocity profile. It is a line that expresses the velocity change from the bottom to the top. So we observe that as the shearing force is moving these layers towards the right hand side, there is also a resistance force that is acting in the opposite direction to the shearing force, and it also acts in a direction parallel to the surface between the layers. Now this resistance force is the measure of this property that we are going to examine called viscosity. Now we have all observed different types of fluids. For example, water flows fairly easily. So again, if you are imagining that water was actually made up of these single layers, the resistance to the movement of these layers towards, say, right hand side is fairly easy. There is not much of resistance. Whereas if you replaced water with, say, honey, you know that the opposing force to the shearing force is going to be quite high, and that's why honey does not flow that easily as water will. So the term viscosity, which is the measure of that flow, will tell us something about the difference between the flow characteristics of water as we compare it with another fluid, for example, honey. So now let's take it one step further to get a quantitative measure. In this velocity profile, we will expand this to develop a mathematical relationship. So we have the vertical line here expressed as AC, and after application of the shearing force, let's say that point C moves to point C dash. In other words, it moves by a distance delta x. And so the vertical line AC is now deflected to AC dash, and that angle of deflection is delta theta. And also, let's say that the distance between A and C is dy. So now you know from your trigonometry that tangent of delta theta is delta x divided by dy. Now if the angle of deflection is fairly small, then we can say that tangent delta theta is about equal to delta theta. Therefore, delta theta then equals delta x over dy. So next we can express that linear displacement delta x in terms of the velocity, because you know that velocity is distance over time. So we can say that delta x, this linear displacement, equals du, which is the small change in velocity, times delta t. So now we can substitute this delta x in our previous expression and get delta theta equals du delta t over dy. So this equation now tells us that this angular displacement not only depends on the velocity as well as the separation between the plates, but also depends on the time. So in case of fluids, we must correlate our shearing stress with the shearing rate. So it is not only the force that is being applied, but also we have to consider the time. So the rate of shear, which is be expressed as Greek letter gamma, and we'll put a dot on it, that will equal the limit of delta theta over delta t. Now delta theta, remember, was the deflection of that line from AC to AC dash, and we are saying that that deflection divided by the time it takes for it to deflect is the rate of shear. And again we put that dot because this term has time. So then we can replace this delta theta from what we obtained earlier, which was du delta t over dy divided by delta t. So delta t will cancel out and gamma dot will equal du over dy. So the shear rate then is the change in the velocity divided by the distance between the plates. So it is du over dy. And Newton observed that when you increase the shearing stress by increasing, of course, the force. Remember, stress is force per unit area. So anytime you increase shearing stress, then the rate of shear, this gamma dot, will also increase in direct proportion. So the shearing stress, which we give a symbol sigma, so sigma is directly proportional to gamma dot. This is again based on Newton's observation. And so we can say sigma is proportional to du over dy. Now, if we remove the proportionality factor, then we have to introduce a constant. And of course, we want to do that, so we have an equation that we can use in solving problems. So sigma equals mu, so mu is the constant, du over dy. Now mu is called the coefficient of viscosity, and this is what gives us an indication of the flow behavior of the fluid. Now Newton is the one who first observed this, the direct proportionality. So for all types of fluids that have this direct proportionality between shear rate and shear stress are called Newtonian liquids. So water is a Newtonian liquid, milk is a Newtonian liquid, juices are Newtonian liquids, and so on. So if we want to plot this shear stress versus shear rate, we get a straight line based on our equation, and the slope of that straight line is mu. Remember the equation of a straight line, y is equal to mx plus c, where m is the slope. So here y is sigma and x is du over dy. That is what we have in our plot, and the slope is mu. So mu is the viscosity. Again, this is true for all Newtonian fluids. In a separate module, we will look at certain fluids that do not follow this linear relationship. They are called non-Newtonian fluids. So let's look at the units of viscosity. Remember that shear stress equals force per unit area. So it is Newton per square meters. We also call it Pascal. And the shear rate is du over dy. So the unit for du which is velocity, is meter per second, and dy is the distance, so that's meters. So meter will cancel out. So the units of shear rate are 1 over second. Now If we substitute that into our equation for viscosity, units of viscosity are Pascal divided by per second. So in other words, that is a 1 over second, and we can rearrange to get that second in the numerator. So the units of viscosity are Pascal second. Now we can look at some values of different types of fluids, and we find that viscosity of air is very small. It's 10 raised to power minus 5 Pascal second, whereas the viscosity of water is 10 raised to power minus 3. Viscosity of olive oil is 10 raised to power minus 1, and viscosity of honey is 10 raised to power 1. So we have quite a variation of viscosities of Newtonian fluids that tells us something about the flow behavior characteristics.